the time you're free. Then we have notes, the ultimate comprehensive book with CBME based question and answers in MCQs. And also we have MCQs specially curated to cater to all the public from the beginner level to the expert level. Apart from that, we have personalized counseling sessions. So you can book a slot for your personalized counseling session anytime with us for any extra support that you need, apart from the academic guidance that we're already providing. We have three different kinds of subscription plans, starting from basic and going up to premium. And they are for 3 months, 6 months, and 12 months, respectively. You can get an additional 20% off if you use my promo code as displayed on the screen. You can see. I think it will be better if you go for the premium plan, because there you have live sessions and clarification where you can clarify your doubts, and also you have personalized guidance as well. Okay. So let's begin with our class, that is electron transport chain, ETC in short. So beginning with the clinical case, a student takes some tablets she's offered at a disco, and without asking what they are, she swallows them. A short time later, she starts to hyperventilate and becomes very hot. What is the most likely action of the tablet she has taken? So your options being an inhibitor of mitochondrial ATP synthesis, an inhibitor of mitochondrial electron transport, an inhibitor of the transport of ADP into mitochondria to be phosphorylated, an inhibitor of the transport of ATP out of the mitochondria into the cytosol, and an uncoupler of mitochondrial electron transport and oxidative phosphorylation. So it's a little tricky question, but become very easy to solve once we are done with our lecture on electron transport chain. The options are also very similar. So in these kind of questions, you need to read the options very well before marking the answer. Okay. Moving forward, let's begin. So electron transport chain, ETC, is a series of redox couples arranged in ascending order of redox potential. So before I explain you this, you need to know a couple of terms. Firstly, what is oxidation? I know all of you must be knowing this, but still, for the sake of recapitulation and easy learning, I'll tell you what is oxidation. So oxidation in simple words is loss of electrons. So when a molecule or an atom or a compound, whatever, it loses electron, de-electronation is taking place, there's loss of electrons, we say that particular compound has been oxidized or oxidation has taken place. Now what is reduction? It's just the contrast of it, the opposite of it, that is gain of electrons. So gain of electrons, when a particular atom or a molecule gain electrons, we say it has been reduced or reduction has taken place. So loss of electron is oxidation. Also one pro tip, when you like learning two contrasting traits, so don't try to learn both of them. Okay, just learn one of them in order to avoid confusion. Like if you learn just loss of electrons is oxidation, so you automatically will know what is reduction. And similarly, like if you know, then when glucose is gone, then the hormone active is glucagon. So you automatically will know that when is insulin being active, that is in the well-fed state. Okay. So when there are two contrasting traits, just try to learn one of them in order to avoid confusion. Okay. So oxidation, coming back to it, is loss of electrons, and reduction is gain of electrons. Now another term we come across is redox couple. Now, what are redox couple? Redox couple are compounds that can exist in oxidized as well as in reduced state. Okay, so redox couple, they are compounds that can exist in oxidized as well as reduced state. For example, all of you know it, NAD plus, NADH. Okay, so your NAD plus is the oxidized state, because you can see the electrons have been lost from it. Okay, and NADH, it has gained electrons, so this is the reduced state. Similarly, you have the example of FAD plus and FADH2. So FAD plus is the oxidized state and FADH2 is the reduced state. So now we know what are redox couples. Okay, redox couple, they are compounds that can exist both in oxidized as well as in reduced state. Now another term that we see here is redox potential. Now what is redox potential? It is the ability to gain electrons. Okay, ability to gain electron. So more is the redox potential, more is the ability to gain electrons. Now let's read the sentence again. So electron transport chain is a series of redox couple, that is compounds that can exist both in produced and oxidized state, arranged in ascending order of the redox potential, that is arranged in increasing order of the ability to gain electrons. Okay, so this is the basic principle of electron transport chain. I'll give you an example to make it even more clear. Now let's suppose there are two redox couple. Okay, let's suppose there are two redox couple, A and B. Now let's assume the redox potential, that is the ability to gain electron. Okay, so the redox potential of A is less than the redox potential of B. So what I'm trying to say is that the ability of B to gain electron is more when compared to the ability of the redox couple A to gain electrons. Okay, so electron from redox couple A will jump to B. Okay, obviously because I'm saying the redox potential of B is more. And what is redox potential? It is the ability to gain electron. So if like this is your A and this is your B redox couple, and I said the redox potential of B is greater than the redox potential of A. So the electron, if A has an electron, it will jump from A to B because B has a greater ability to gain electron when compared to A. And this is exactly ETC works on this principle. Okay, now is it clear? Let's read this again. Electron transport chain is a series of redox couples arranged in ascending order of their redox potential. So what we are trying to say is that electron transport chain, in this chain, you have redox couples. They are arranged in such a way that they are in increasing order or ascending order of the redox potential. So after like the first redox couple will have a redox potential lower than that of the next, or we can say vice versa, that the next redox couple in the series will have a redox potential higher than that of the previous one. So what happens is that these are your redox couple. For example, these are your redox couple. So the electron will jump from the previous redox couple to the next, to the next, to the next. This is exactly what happens in electron transport chain. Okay. Now, when electron jumps from lower redox potential to higher redox potential, it is an exergonic reaction, that is free energy is liberated. Now what is saying that when this jumping is taking place, when electrons are jumping from a lower redox potential to a higher redox potential, along with this is energy is released. This is an exergonic process, and in this jumping of electrons, energy is also released. Okay, so that was the introduction about electron transport chain. Now let's see the concept of electron transport chain. So, reducing equivalents that are generated via different pathways like glycolysis, TCA, etc., they enter electron transport chain and generate ATP. So, whatever reducing equivalents are being generated in your body, like we have seen in TCA, FADH2 NADH was being generated. In glycolysis, we have seen NADH was being generated. So, all of these reducing equivalents, they enter electron transport chain to generate ATP. Okay. So it's trying to say I'll give you a simpler diagram. This bookish one might seem a little confusing. So it's basically trying to say, like from your whatever food you've taken, whatever macromolecules are present, like your carbohydrate, protein, lipid. We also discussed this in our previous lecture as well. So all of these, they metabolize and finally converge into what? Acetyl CoA. Remember, your carbohydrates via glycolysis was forming pyruvate, and then pyruvate via link reaction was forming acetyl CoA. Similarly, your ketogenic amino acids, they were being catabolized into acetyl CoA, and then your lipids from there, the fatty acid was undergoing beta oxidation to form acetyl CoA. So ultimately, whatever food you've taken from there, they're all converging into acetyl CoA via various pathways, and this acetyl CoA was entering TCA. So we've studied about TCA. Now the next step is in the TCA, what was being generated? You're reducing equivalence. That is NADH we had studied was being generated, and FADH2 was generated in one of the steps. Now these reducing equivalents, now they enter where? They enter this electron transport chain. Okay, now in this electron transport chain, what is happening? These reducing equivalents, they are oxidized into NAD plus and FAD plus respectively. So they are oxidized. And also at the same time, what is happening? ATP is being generated. So your ADP changes into ATP. So ATP is being generated. So what is this known as? Phosphorylation. That is production of ATP. So this is basically an overview of your electron transport chain. So in electron transport chain, two processes are taking place. First is oxidation of reducing equivalents, and the second is phosphorylation, that is generation of ATP. Okay, so two processes takes place, oxidation of reducing equivalents and phosphorylation. Thus we say oxidation is coupled with phosphorylation. You can see how they are coupled. The two processes are coupled in electron transport chain. On one hand, there is oxidation of reducing equivalents taking place, and on the other hand, there's phosphorylation taking place. Therefore, ETC is oxidative phosphorylation. Okay, this is what the diagram is trying to say. From the food, you get your fats, carbohydrate, proteins. They are finally absorbed and into their monomeric forms. They are broken down. That is your fatty acid, glycerol, glucose, and everything. And then it's all converging into acetyl CoA and entering into TCA. And then from there, they enter into respiratory chain. That is your electron transport chain. Okay. Okay. Now the location of electron transport chain, it is located in the inner mitochondrial membrane and is arranged in different complexes. Okay. So where are these reactions taking place of the ETC? They are taking place in the inner mitochondrial membrane. So whatever reducing equivalents were generated from our food, we trap them to get ATP, okay? Because ultimately what is happening? See, ATP is being generated. So we get ATP from the reducing equivalents generated from the food. This was your food. This was metabolized and it converged into acetyl CoA. It entered TCA, and in the TCA, reducing equivalents were generated. So basically, these reducing equivalents are generated from the food we had, okay? And then ultimately, it is entering the electron transport chain to give what? To give ATP. So we can say we get ATP, we get energy from the reducing equivalents that were generated from the food that we had. Okay, now what are the components of the electron transport chain? Electron transport chain components. Just present in the inner mitochondrial membrane as we discussed. Okay, so there are two types. They are fixed. It can be divided into fixed, which are 5 multi-protein complexes. Okay, that is complex 1, complex 2, complex 3, complex 4, and complex 5. We'll talk about each one of them in detail. And apart from that, we have 2 mobile carriers. That is your coenzyme Q, and cytochrome C. Okay, so these are the mobile carriers, the mobile part of the electron, components of the electron transport chain, and the fixed components are your 5 multi-protein complexes. Okay, so in this diagram, you can see your NADH, it gives us electron to complex 1, and your succinate, it gives its electrons to complex 2. Okay, and both of them, they give it to Q. Now from Q, the electron goes to complex 3. Via complex 3, it goes to cytochrome C, and from cytochrome C, it goes to complex 5, and then complex 5 ultimately gives the electron to oxygen, and this oxygen is reduced to water. So this is the overall view of the electron transport chain. Okay, how the electrons from NADH or FADH2 are being transferred, and ultimately they are given to oxygen, and this oxygen is reduced into water. Now let's take each of the complex one by one in detail. So your complex 1 is fixed, as we've already discussed. In complex 1, producing equivalent NADH gives electron and is converted to NAD+. Okay, so after giving its electron, that is, there is loss of electron. So what will happen? Your NADH is oxidized to NAD+. And who receives this electron? So the electron that is given by NADH, it will go via complex 1 to coenzyme Q. So it is reaching coenzyme Q via complex 1. So the complex 1, it takes electrons from NADH and then it gives it to who? Coenzyme Q. So your coenzyme Q, it is receiving electrons. So it gains electrons, and on receiving electron, it gets reduced. And your NADH, it gives electrons, so it gets oxidized. Therefore, complex 1 is also known as NADH Q oxidoreductase, because your NADH is getting oxidized. Why is it getting oxidized? Because there is loss of electrons. It gives its electrons. Electrons are lost from NADH to complex 1, and then this complex 1 gives it to coenzyme Q. Okay, and then coenzyme Q, it gets reduced because it gains electrons. Okay, so it gains electrons, so it gets reduced. Therefore, the name of complex 1 is also NADH Q oxidoreductase, because your NADH is getting oxidized and Q is getting reduced. It is also known as NADH hydrogenase. Now, the components of complex 1 are FMN and iron sulfur complex. Okay, so your electrons from NADH goes to complex 1, and in complex 1, it is first accepted by FMN, changes into FMNH, and then it goes to iron sulfur complex, and then from this it is taken up by coenzyme Q. Need not go into so much detail that each acceptor within the complex, it's okay, you can just skip that. Just know that electrons from NADH, they are taken up by complex 1, and then complex 1 gives it to coenzyme Q. So ultimately NADH is getting oxidized and coenzyme Q is getting reduced. So that was about complex 1. Now coenzyme Q. What is coenzyme Q? It is a lipid. Okay, so it is the only, this is important, only non-protein component of electron transport chain. Sometimes you might get asked in an MCQ that which of the following components of component of electron transport chain is not a protein. So your answer will be coenzyme Q. It is a lipid and the only non-protein component of electron transport chain. It is a mobile carrier. Okay, so this is not fixed. Also known as ubiquinone or Q10, because it has 10 isoprene units. Okay. So if I show you this transfer in the form of a diagram, maybe it will be easier for you to understand. Okay, so let's assume this is complex 1. and this one is coenzyme Q. Okay, so what is happening is NADH gives its electron to complex 1 and gets oxidized to NAD plus. Now, from this complex 1, this enzyme is given, this electron is given to coenzyme Q. So, coenzyme Q on gaining electron gets reduced and this gets oxidized. Okay, this is via the help of this small little diagram. You can actually understand that huge stanza. Okay, so this is the power of diagrams and flowcharts. This is very simple. I think now you can understand. Okay, now moving forward to complex 2. It is a part of enzyme succinate dehydrogenase. We've also studied this in TCA. Okay, the TCA, this was succinate dehydrogenase was the only enzyme of the TCA which was not present in the mitochondrial matrix. It was present in the inner mitochondrial membrane as it was part of complex 2 of electron transport chain, remember? And what was the function role of succinate dehydrogenase? It was involved in conversion of succinate to fumarate. So it converts succinate to fumarate. Now, complex 2, it receives electrons from succinate and gives it to coenzyme Q. Okay, so you see, complex 1 has been bypassed here. Succinate is directly giving its electrons to coenzyme Q. Succinate is being oxidized because succinate is giving its electrons, so it is getting oxidized. There is loss of electrons, and coenzyme Q is gaining electrons, so it is getting reduced. Therefore, complex 2 is also known as succinate Q oxidoreductase or succinate Q reductase is another name for it. The components of complex 2 include FAT and iron sulfur complex. Okay. This also will be easy for you if I represent it in the form of a diagram. Okay, now let's suppose this is complex 2 and this is your coenzyme Q. So succinate gives its electron to complex 2 and changes into fumarate. Okay, so on giving its electron, it becomes oxidized because it has given its electron, so it gets oxidized. Okay, now this electron from complex 2 jumps to coenzyme Q. So this electron has reached and coenzyme Q on gaining electrons, it becomes reduced. Okay. Now electron, so we see that electrons from NADH, they were given to complex 1. But electrons from FADH2, they are directly enter electron transport chain at the level of coenzyme Q. So this step does not liberate enough energy to act as the proton pump. We will see that these complexes, when the electrons are jumping from one complex to the other, we have already studied that it is an exergonic process. So energy is being released. Okay. This energy is used to pump electrons. So they act, all the complexes, they act as proton pumps. Later we will study this in detail. But here for now, I'm telling you that the energy released from complex 2, it is not enough for it to act as a proton pump. Okay. Now, three major enzyme systems that transfer the electron directly to coenzyme Q. One we've already spoken about, that is succinate dehydrogenase. The other two being fatty acyl-CoA dehydrogenase and your mitochondrial glycerol 3-phosphate dehydrogenase. Okay, so these are important. Maybe I should write it down so that you remember. So three major enzyme systems that transfer the electron directly to coenzyme Q. That is your complex 1 is bypassed. Okay. 1 is your succinate dehydrogenase. The other being fatty acyl CoA dehydrogenase and mitochondrial glycerol 3 phosphate dehydrogenase. Okay. So FADH2 will be giving its electron to complex 2 or directly to coenzyme Q. Complex 1 will be bypassed and NADH will give its electron to complex 1. Okay. And also the when the electrons are jumping from one complex to the other, we have said that it is an exergonic process and energy is being released during this process. Okay. But the energy released from complex 2, this is not enough to act as a proton pump. We will see what is a proton pump and all that later on. Okay. But for now, just remember that your complex 2 does not act as a proton pump, whereas your complex 1 does act as a proton pump. Okay. So till now, I hope it's clear. Moving on to complex 3. So electron from coenzyme Q will jump to complex 3 and from complex 3, they jump to cytochrome C. So coenzyme electrons from coenzyme Q, they are jumping to cytochrome C ultimately via complex 3. So your coenzyme Q is getting oxidized now. Okay, coenzyme Q is getting oxidized and your cytochrome C, it is gaining electron. So it's getting reduced. Cytochrome C, it gains electron and your coenzyme Q, it loses electron. So there's loss of electron. Therefore, complex 3 is also known as Q cytochrome C oxidoreductase. Now, the different components of complex 3 are cytochrome B, cytochrome C1 and risky iron sulfur complex. So the other name for this complex is also cytochrome B C1 complex. Okay. Explaining this via the diagram. So, okay. Now, let's suppose this is coenzyme Q. This is your complex 3 and this is your cytochrome C. So, your coenzyme Q, it has received electron from complex 1 and complex 2. From complex 1 and complex 2, it has received electrons. So, it was what? It was reduced up till now. But now we are saying that electrons from this coenzyme Q via complex 3 is given to cytochrome C. Okay. So, this gets oxidized, your coenzyme Q, because there is loss of electrons. It is giving its electron to whom? Via complex 3, it is giving to cytochrome C. So cytochrome C is gaining electron, so it is getting reduced. Okay. So I hope this is clear. Now moving forward to complex 4. Now this complex 4, it receives electron from cytochrome C and then this electron is given to oxygen. So cytochrome C is oxidized because it is giving its electron. So cytochrome C is oxidized and oxygen is reduced to water. Oxygen should get 2 electrons in order to get completely reduced to water. Okay. After receiving 1 electrons, what it forms superoxide ions. Okay. So in order to avoid that, it should receive 2 electrons. Okay. After receiving 1 electron, it forms what? Superoxide. Okay, which is highly reactive, okay, and damaging. So if oxygen, it receives only 1 electron, it will form superoxide anion. Therefore, And oxygen should receive two electrons to be completely reduced to water. So the negative charge on oxygen, it will attract hydrogen ions from the surrounding and be reduced to water. Water is formed. Okay. So your oxygen, so who is the final acceptor of your electron? So final electron acceptor is oxygen. So we've seen how electrons from NADH or FADH2 through different complexes finally reach complex 4, and then this complex 4 gives the electron to the final acceptor, which is oxygen, and then this oxygen is reduced to water, and this is an irreversible complex, and the components of this complex are heme AA3, which is also known as cytochrome AA3, or copper A, copper B center. Okay, so that was about complex 4. Let's recapitulate it quickly. See, NADH gives its electron to complex 1. Your succinate, FADH2, they will be giving its FADH2. Okay. Your succinate dehydrogenase, mitochondrial glycerol 3-phosphate dehydrogenase, and fatty acyl CoA dehydrogenase. They all give the electrons via complex 2. In this case, complex 1 is bypassed. Okay, ultimately what is happening? Your coenzyme Q is receiving electrons and it gets reduced. Now this coenzyme Q, it gives its electron to cytochrome C via complex 3. Now this cytochrome C gives its electron to complex 4, and this complex 4 gives its electron to oxygen, and this oxygen, it receives 2 electrons to be completely reduced to water, because on receiving 1 electron, it leads to the formation of superoxide anion. Okay, so this was briefly about electron transport chain. We've taken each of the complexes in detail. Okay, let's take one of the MCQs. That is, the final acceptor of electrons in electron transport chain is, so now we all know it is oxygen. Okay, now there's another complex 5. Okay, now this complex 5, it is ATP synthase. It is the smallest molecular motor present in our body. Now, the components of complex 4, so it has two subcomplexes. It has two components, that is, one is F0 subcomplex and the F1 subunit. Okay. What is the F1 subunit? It is made up of 10 C disc proteins. They are hydrophobic. They span inner mitochondrial membrane and they act as proton channels. Okay. Talking about the F1 subcomplex, they are made up of 9 subunits. What are those 9 subunits? There are 3 alpha, 3 beta, 1 gamma, delta, and 1 epsilon. So they make up the 9 subunits of the F1 subcomplex. Now your gamma subunit, it forms the bent axial which joins the F0 and the F1. And gamma is also the rotatory subunit. So not the entire of ATP synthase rotates. Okay, your entire ATP synthase, that is your complex 5, we will see will not rotate when there is phosphorylation taking place. It is only the gamma which is the rotatory subunit. Okay. So not the entire ATP synthase rotates. Okay, so now let's have a look at the diagram to make it more clear. Okay, so it says this is your F0 subunit. You can see these 10 C disc proteins. You can see them here. Okay, so this forms your F0 subunit, and you can see this is present in the inner mitochondrial membrane. Now, this is protruding into the matrix, and this being your F1 subunit. And you can very well see that it has 1, 2, 3 alpha, 3 beta subunits, and you can see this 1 gamma which is forming the bent axial. As you can see, you can appreciate this bent axial here. This gamma is forming the bent axial, and it says that this gamma is involved in the rotation. Okay, not the entire. Now this is what I was saying, not the entire complex 5, that is this entire structure will not move. Only the pentaxle gamma will move. And you'll also see that these C proteins also move. Okay. So not the entire ATP synthase moves. When phosphorylation takes place, only gamma will be moving. So that is why we say that gamma is the rotatory subunit. And then you can also appreciate this delta here. Epsilon is also there, present on the bent axle, but it is not shown here in the diagram for the sake of convenience. Okay, so that the diagram for clarity, it is not shown in the image, but epsilon is also there, epsilon protein. So this is about your complex 5. Okay, let's take a MCQ. Electron transport chain involves all except NADP, NAD, coenzyme Q, FAD. So we know that what is not involved? NADP is not involved. NADP is involved where? It is involved in productive biosynthesis of steroid hormones and all that, fatty acid synthesis. Okay, you've studied in HMP. Okay, now moving on to what is oxidative phosphorylation. So it includes your oxidation phase and phosphorylation phase. So till now we have seen how the reducing equivalents that were generated from food, they were passing through the electron transport chain, jumping from one complex to another complex. The principle being that your complexes are arranged in ascending order of their redox potential. Okay. And ultimately they are taken up by oxygen, and oxygen is reduced into water. Now let's move forward that what is oxidative phosphorylation. Okay. So in the oxidation phase, electrons jump from one complex to another. Exactly what we discussed. Okay. For example, if we take the path of NADH electron. So NADH will give its electron to complex 1. Then from complex 1, it goes to coenzyme Q. Then from coenzyme Q via complex 3, it is taken up by cytochrome C. And then your cytochrome C, this gives the electrons to complex 4. And then complex 4 finally gives it to oxygen. Okay. And also, it studied that your coenzyme Q and cytochrome C, they were mobile carriers. So your complex 1 is fixed, your complex 3 is fixed. Coenzyme Q will go to complex 1, take electrons from there, then go to complex 3 and give electrons to it. Okay. Similarly, cytochrome C, it goes to complex 3, picks electrons from there, and then goes to complex 4 and gives electron to it. So your complexes are fixed and your mobile carriers being coenzyme Q and cytochrome C. And also you must have noticed that your complex 2 is not found after complex 1. See, this is your complex 1 and this is your complex 3, and in between you have coenzyme Q. So your complex 2 is not found after complex 1. Okay. This is your complex 2 because all your complex 2 is directly giving its electron to coenzyme Q. You can see here, and then coenzyme Q gives it to complex 3. And both of them from here and here, you can see they're giving it to cytochrome C, and this gives it to complex 4. Okay. Okay. Now let's take the oxidation phase. So what is the oxidation phase? The electrons jump from one complex to another. So this releases free energy. It is an exergonic process. This free energy released is used for the pumping of protons to the intermembrane space. So basically what it is trying to say is, let's suppose this is your mitochondria. So these are your complexes. Okay. So what is happening when electrons are jumping? Okay, this is like the diagram is not to scale. This is only for explanatory purposes. Okay. So when electrons are jumping, what is happening? Free energy is being released. So this free energy that is being released, it is used to pump protons. Okay. So from the matrix, what is happening? Your protons are being pumped into the intermembrane space here. Okay, like this. Okay, now have a look at this diagram. This is what I was trying to make. Okay, these are your complexes, complex 1, 2, 3, 4 and all. And what is happening? You can see your electrons are jumping, and here you can see protons are being pumped out from the matrix to the intermembrane space. So that energy that is released due to the pumping of electrons, it is used to, due to jumping of electrons, it is used to pump protons into the intermembrane space. So electrons jump from one complex to another, and along with it, the complex pumps proton to the intermembrane space. So your complex 1 pumps 4 protons, complex 3 also pumps 4 protons, and your complex 4, it pumps 2 protons. So a total of 10 protons are pumped when NADH electron is jumping. So if you have a look at this diagram, so your complex 1, your NADH gives its electron to complex 1, and this complex 1 gives it electron to coenzyme Q. So when this electron jumps from complex 1 to coenzyme Q, energy is released, and that energy release is used to pump protons from complex 1 outside into the transmembrane space. So this complex 1, it pumps 4 protons from the matrix into the intermembrane space. So this complex 1 is acting as a proton pump, we can say. Similarly, with complex 3 also pumps 4 protons. And your complex 4, it pumps 2 protons. And remember, I told you when we were talking about complex 2, I said your complex 2, it does not act as a proton pump. So your complex 2 does not act as a proton pump. Okay, it does not act as a proton pump. Why? Because the energy that is released from complex 2 is not enough to pump the protons. Okay. Okay. Now moving on to the phosphorylation phase. So when electrons are jumping, free energy is released, and that free energy released is trapped to pump protons. Okay, in other words, it is trapped to form ATP. So your electrons are jumping from one complex to another, which is releasing free energy, and that free energy which is released, it is used via the complexes to pump protons from the matrix into the intermembrane space. And here the numbers are given, that is your complex 1 pumps 4 protons, complex 3 pumps 4 protons, complex 4 pumps 2 proton, and also complex 2 does not act as a proton pump. Okay. Now the phosphorylation phase. A potential difference is created due to pumping of protons as positive charges accumulate. Okay, so from the matrix, you are pumping the hydrogen ion, you're pumping electrons into the intermembrane space. So obviously, what will happen? Your positive charges, they are accumulating in the intermembrane space. So what happens? Your mitochondrial matrix, it is less positive, and your intermembrane space is becoming more positive due to accumulation of positive charges, and this creates a potential difference or a potential gradient. Okay, so what happens? Your protons, they move into the matrix to the F0 subunit. Okay, so your protons are accumulated, or positive charges have accumulated in the intermembrane space. So from that intermembrane space via the F0 subunit, those protons, they enter into the matrix. Now, what happens? This causes the rotation of the gamma subunit. Okay, let's refer to this diagram back. Okay. Now, what happens is, you can see this hydrogen ion. So, when there is, this is the outside, this is the intermembrane space. So, positive charges have accumulated here. Now, what happens? This enters via the F node, this F node subunit, it enters into the matrix here on the inside. And while it is entering through the F node subunit into the matrix, what happens? It is accompanied by rotation of the gamma subunit and the F naught C disks. Okay. So there is rotation of the gamma subunit along with the F naught. Now this rotation of gamma produces conformational changes in beta subunit. Okay. So when the gamma rotates, conformational changes take place in the beta subunit, leading to the conversion of ADP into ATP. Okay. So each of the three beta subunit convert ADP into ATP, and this is what is known as phosphorylation. So your ATP has been generated. So jumping of electrons is oxidation. And when ATP synthase complex rotates, conformational changes take place in the beta subunit and it converts ADP into ATP, which is known as phosphorylation. And thus we say that oxidation is coupled with phosphorylation. And this theory is known as chemiosmotic theory, and it was given by Peter Michel. Okay, I hope it's clear. Very important, because it's very simple. I've repeated it so many times that I think not just clear, but you must have memorized it. Okay. Once again, before I begin with the inhibition, okay. Your complexes are arranged: complex 1, coenzyme Q, complex 3, complex 4. They're arranged in, these are all redox couples, and they're arranged in ascending order of their redox potential, that is their ability to gain electrons. So what happens is your NADH will be giving electrons to complex 1, and then those electrons via complex 1, they are taken up by coenzyme Q, and then the cycle continues that from coenzyme Q, the electrons via complex 3 goes to cytochrome C, and then cytochrome C gives them to complex 4, and then the final acceptor being oxygen, and then oxygen is completely reduced to water by gain of 2 electrons. Okay. And your FADH2, it gives you the electron directly to coenzyme Q. Complex 1 is bypassed. And also I said that when the jumping of electron takes place, this is known as oxidation, and this oxidation is coupled with phosphorylation. What is phosphorylation? I said that when the electrons are jumping, it is accompanied by, it is an exergonic process, that is energy is being released. So the free energy that is released, it is used to pump protons from the matrix into the intermembrane space. So what happens? Your positive charges are accumulating in the intermembrane space. So this leads to generation of a potential difference. The positive charge in the matrix is less compared to the positive charge in the intermembrane space. So these protons, they via the F naught subunit enter into the matrix, and while they're entering into the matrix, it causes the rotation of the gamma subunit of the complex 5, that is ATP synthase. So when the gamma subunit rotates, it brings about conformational changes in the beta subunit, leading to the formation or conversion of ADP into ATP, and which is known as phosphorylation. So we see how oxidation, that is jumping of electrons, is coupled with phosphorylation, that is generation of ATP. Okay. Now moving on to the inhibitors of electron transport chain. And also, this also explains, before I begin with the inhibitors, this also explains when we say that your NADH, it enters into electron transport chain and it gives 2.5 ATP. And we say that FADH, it gives 1.5 ATP in electron transport chain. Why? Because your complex 2 does not act as a proton pump, and also complex 1 is not involved. So in FADH2, only complex 3 which is pumping 4 protons, and you have complex 4 which is pumping 2 protons. Okay, so 4 protons per ATP synthesized. So if for 1 ATP to be synthesized, 4 protons have to be pumped. So for 4 protons are pumped, you synthesize 1 ATP. Okay, I'll just write it down to make it clear. This is what I'm trying to explain. This is your NADH. Okay. NADH gives it electrons to complex 1, and then it is taken up by coenzyme Q, and then it gives it to complex 3, and then to cytochrome C, and then to complex 4, and then your complex 4, it gives 2 electrons to your oxygen, to form water. Okay. Now what I'm trying to say is that your complex 1, it acts as a proton pump. So it acts as a proton pump, and I told you that it pumps 4 protons. Okay. Your complex 3 also acts as a proton pumps and it pumps 4 protons, 4 hydrogen atoms. And your complex 4 also pumps 2 hydrogen. Now, for every 4 proton pumped, 1 ATP is synthesized. Okay. So, in case of NADH, there are 4, 4, 8, 9, 10. 10 protons pumped, so you get 2.5 ATP synthesized. Okay, so this was for NADH. Now, for FADH, I'm saying FADH2, it will be entering via complex 2, okay? And complex 2, I say it does not act as a proton pump. So, no hydrogen pump, so no ATP formed, okay? Now, it gives it proton to coenzyme Q, and then it gives to complex 3, and then from complex 3 to cytochrome C, and from cytochrome C to complex 4. So, complex 3 will pump 4 protons, which means 1 ATP, and complex 4 pumps 2 proton, which means 0.5 ATP. So for FADH2, we get 1.5 ATP, that is 1 ATP less than FADH2. Okay. Okay. Now let's begin with the inhibitors of electron transport chain. Now the inhibitors, they can be inhibitors of electron transfer, they can be inhibitors of oxidative phosphorylation or uncouplers. So inhibitors of electron transfer. So electron transfer is occurring at the complexes. So the inhibitors of electron transfer are inhibitors of the complexes. Okay. Now complex 1 inhibitor, fish poison known as rotenone, amobarbiturol, which is a barbiturate, and puricidin A, that is an antibiotic. So these are the inhibitors of complex 1. So your NADH gives its electron to coenzyme Q via complex 1. So in this case, there is inhibition at this level, okay? And these are the inhibitors of complex 1. Now, phenobarbiturone inhibits which of the following complex of electron transport chain? So, complex 1, complex 2, 3 or 4. So, your answer will be complex 1, okay, because it is a barbiturate. Now, complex 2 inhibitors, they are malonate, carboxyn, and trienol trifluoroacetate. Okay. Now, complex 2, we know that your FADH2 was giving its electron to complex 2, which gives it to coenzyme Q. So the block is here at this level. The inhibition is here at this level. Okay, and we've already known that succinate dehydrogenase is a part of complex 2. Okay, your succinate dehydrogenase is a part of complex 2. And remember, while studying TCA, I said that succinate dehydrogenase is inhibited by malonate. So obviously, one of the inhibitors of complex 2 will be malonate. Okay. Now moving on to complex 3 inhibitors, they are British anti-leucite and antimycin A. Complex 4 inhibitors being carbon monoxide, cyanide, and hydrogen sulfide. These are all gases, okay, and sodium azide is also one of the inhibitors of complex 4. Moving on to one of the MCQs, mechanism of cyanide poisoning. So your What is the mechanism of cyanide poisoning? The options are inhibition of cytochrome oxidase, inhibition of carbonic anhydrase, inhibition of cytochrome C, or inhibition of ATP synthase. So remember, I told you that cytochrome oxidase is another name for complex 4. So cyanide poisoning, it inhibits your complex 4, which is also known as cytochrome oxidase. Now moving on to inhibitors of oxidative phosphorylation. Oxidation will take place, but it is not coupled with phosphorylation. Okay. So these inhibitors, the phosphorylation is affected. Okay. And phosphorylation was taking place by the complex 5, that is your ATP synthase. Okay. So these inhibitors, they cause blockage of complex 5 onwards. Okay. Because before that, complex 1 to 4, they are involved in oxidation. Your complex 5, that was the ATP synthase, that was involved in phosphorylation. So the blockage needs to be in complex 5 onwards. So your F naught is blocked, protons will not be pumped back into the matrix. So if F naught is inhibited by oligomycin and venturecidin, your F1 is inhibited by orovertin, and your ADP ATP transporter is inhibited by etractyloside. Okay, so there are oligomycin and venturecidin and orovertin and etractyloside. So your blockage is at complex 5. Your oligomycin, it completely blocks both oxidation and phosphorylation. Okay, and what is ADP ATP transporter here? This. So your ADP, it should go into the inner mitochondrial membrane and be converted into ATP. Okay, we know that your ADP is changing into ATP. So for that, you need ADP. So your ADP should enter into the inner mitochondrial membrane, and that ATP that is formed, it has to go out. So it should leave the mitochondria. So this is taking place, as we know, the inner mitochondrial membrane is impermeable. So this is taking place with the help of a transporter, that is ADP ATP transporter. Okay, because your ADP or ATP, it is not permeable to inner mitochondrial membrane and it needs a transporter. So if the transporter is blocked, oxidation happens, but there is no phosphorylation taking place. Okay, and this transporter is blocked by etractyloside. So your F0 F1 complex ATP synthase inhibitor is etractyloside, oligomycin, antimycin, and protein. So your answer will be oligomycin. Etractyloside will not be your answer because it is blocking the ADP ATP transporter. Okay, so your answer will be oligomycin. Now, moving on to uncouplers. Now, what are uncouplers? The uncouplers, they create hole in the inner mitochondrial membrane. So, oxidation happens, but no phosphorylation is taking place. We have seen that there was a potential gradient, okay? So, your protons were accumulating in the intermembrane space, and that positive charge accumulated there was creating a potential difference, due to which the protons were then entering the matrix through your complex 5. But what happens, these uncouplers, they create hole in the mitochondrial membrane. So instead of the protons entering via the complex 5, because when protons enter via complex 5, then only that complex 5 will be generating ATP. But due to these holes, because owing to the uncouplers, the protons are entering the matrix via these holes. So there is no phosphorylation taking place. Okay. And your potential difference, that potential gradient is also dissipated. Okay. Now, examples of some uncouplers. So chemical uncouplers being 2,4-dinitrophenol, dinitro-cresol, fluorocarbonyl cyanide, phenyl hydrazine, and aspirin hydroses. Having a look at one of the MCQs, dinitrophenol inhibits the electron transport chain by, so cytochrome B inhibits ATP synthesis and electron transport chain. So dinitrophenol, we all know that it is inhibiting ATP synthesis. So you have to have a look at these two options, okay? Now, in these two options, it is saying that it inhibits ATP synthesis and electron transport chain. It inhibits ATP synthesis but not electron transport chain. So your answer will be this one, because there is inhibition of phosphorylation but oxidation is taking place. Okay. So your answer will be C. Now moving on to physiological uncouplers, they are thermogenin, which is present in brown adipose tissue, thyroxine, and long-chain fatty acid. Okay, so what is thermogenin? Your thermogenin is a protein which is present in inner mitochondrial membrane of adipocytes. Okay, your thermogenin is a protein. It is a protein present in inner mitochondrial membrane of adipocytes. And it is involved in, it is responsible for non-shivering thermogenesis. Okay, so what is happening, it provides alternate pathway for protein. So your thermogenin is a physiological coupler. So instead of your protons entering via the complex 5, as it is an uncoupler, it forms a hole in the inner mitochondrial membrane and your protons will enter via this hole. Okay, so it provides an alternate pathway for your protons. Other physiological uncouplers being thyroxine and long chain fatty acid. Now, what are ionophores? Okay, ionophores are, they are lipid soluble compounds that increase the permeability of the lipid bilayer to certain ions. Okay, and they can be of two types. Ionophores, they are lipid soluble compounds which increase the permeability of the lipid bilayer for certain ions. Okay, now they can be of two types. They can either be mobile ion carriers or they can be channel formers. Okay, now example of mobile ion carriers is valinomycin. So your valinomycin, it increases the permeability for potassium. Okay, so your potassium, it allows potassium to permeate the mitochondria and thus it dissipates the potential gradient. Okay, because the positive charge is able to enter the matrix not via complex 5, but because of this ionophore, which is increasing the permeability for potassium. Okay, for the membrane. So your potassium enters it, your valinomycin will allow potassium to enter into the mitochondria and thus dissipating the potential gradient. And the other be your channel formers. For example, your example can be gramicidin. So what is channel formers ionophores? That is, they form channels in the membrane. Okay, they are therapeutic agents called as channel formers. Now, proton channels, they works on the potential gradient difference. Okay, so when there's a potential gradient difference, then only those your positive charges proton from the intermembrane space were entering into the matrix via the F naught. Okay, now what happens? Now let's suppose these potassium channel formers, they form potassium channels. Okay, so your potassium, they is pumped inside via these potassium channels. Okay, now what happens? This nullifies the potential gradient, leading to no potential difference between the matrix and the transmembrane space. So now what will happen? Your proton channel will not work because it is working because of the potential difference only. So ionophores, they are involved in dissipation of proton gradient and thus inhibiting electron transport. Example being valinomycin, gramicidin. Okay, so it is something like this. If I draw a diagram, this was your F naught, which was supposed to work, but because of this ionophore, what happened? It formed a potassium channel. So this potassium, via this potassium channel that is formed by this ionophore, it will enter into the matrix and thus the positive charge here is dissipated. Okay. Now function of brown adipose tissue. So in brown adipose tissue, one NADPH produces 0 ATP because that has thermogenin which inhibits phosphorylation. So your NADPH, it was producing ATP, but what happens? Because in your brown adipose tissue, there's a physiological uncoupler present, that is thermogenin. So your brown adipose tissue, they have an uncoupler which is thermogenin, because of which what is not happening? Your phosphorylation is not happening. So ATP is not being generated. Okay. So what is the function of brown adipose tissue? It is not to generate ATP, but it is to generate heat. Okay. And so function of BAT is to generate heat in hibernating animals and neonates. Now, when the electrons are jumping from one complex to the other, so the free energy that is released, it is not utilized for the production of ATP, but rather it is used to generate heat, okay, instead of ATP. So you must have noticed that the neonates, they have brown adipose tissue in their cheeks and at the back of the neck, just to keep them warm. Okay, so the neonates have chubby cheeks full of brown adipose tissue to prevent hypothermia. So this is the non-shivering mechanism of thermogenesis. Okay, in shivering, what is happening? Muscle contraction is happening and body is producing ATP and generating heat. But here, this is non-shivering thermogenesis. Okay, and this involves your brown adipose tissue and thermogenin. So that was about electron transport chain. And with this, we come to the end of the class. It was an important and a little sophisticated topic. I hope you were able to understand it. If you have any queries, you can send them. Probably we'll be now starting with vitamins from next week. Okay, thanks for watching.